Hello everybody, my name is Simon Cox. I'm a lecturer in mathematics at Aberystwyth University. I'm going to talk to you briefly today about graphical solution of coupled differential equations. Then I'm going to hand you over to my colleague Kim Kenobi, who's going to talk about statistical modelling of a very similar subject. So as Andy has said, if you have questions, I'm trying to keep an eye on the chat, and if you want to ask them, you can do so, but questions for clarification during the talk, and then we can have a proper question and answer session when I've finished, because I hope some of your questions will be answered as I go through the material. So my idea is to illustrate that the solution of ordinary differential equations, and I understand that some of you won't have met differential equations yet, can be found by relatively simple analysis of limiting cases and graph sketching. And so you know that solving equations is difficult, and so I'm going to try and show you some ways to get to a solution, or to understand what the solution is telling you without having to go through that process. That is, without solving these equations explicitly. And so to do that, I'm going to have some context, and the context is some population of individuals who are susceptible to infection by a disease. And now this could be rabbits and this could be people, and you'll all have one idea very clearly in the front of your mind. But the mathematics, of course, and we've seen this list of all the different combination of subjects that people are doing here, and all the different things you want to go on to do. The mathematics that underpins this, of course, is much more general than applying to any one disease and any one population. But as an applied mathematician, I would like to be able to suggest some control strategy to reduce the spread of this disease. The reason I'm talking about this is one of the things that I teach. It's a third year module, one of the more straightforward examples. So in first year, you learn about basic differential equations, but by third year, we're ready to apply them and to use some more complicated examples to try and understand the real world. And so, as you know, real life is complicated, and in mathematics, the art, if you like, of modelling is to try and make some simplifications. And sometimes you go too far, you make your model so simple that it has no predictive power, but that's fine. You've learned something, and then you can go back and change things. So my first assumption, A1, is that within this population, each individual is in one of three categories. Either they're susceptible to catching the disease, that's an S. They may be infected with the disease, that's an I. And they may be immune, and hence they are removed, that's an R, removed from the model. So this is one of a class of models known as SIR models. You're susceptible, infected, or removed. And there's no other possibilities. The second assumption that will make the mathematics easier is that the population is well mixed. That is, any susceptible individual can be infected by any infected individual. And then the third and final assumption is that at some initial time, t equals 0, each individual is either susceptible or infected. No individual has been removed from the model yet. And so what that means is the size of the population is constant, capital N, and in general, it's the sum of S plus I plus R individuals, but at time t equals 0, it's just the sum of S and I, S at t equals 0 plus I at t equals 0. So now we need to write down some mathematical model. And the first thing I want to think about is how the number of susceptible individuals changes. And so clearly, if there are more susceptible individuals and more infected individuals, and they come into contact more often, then we expect the number of susceptible individuals to decrease and the number of infected individuals to increase. So how do we write that as a piece of mathematics? If you've met calculus, you'll recognize this as a derivative. If you haven't, this is the notation we use for the rate of change of S with time, the rate of change of the number of susceptible individuals. And so the first thing I know is that this has to be a negative sign. The number of susceptible individuals is decreasing as they become infected. And then it's proportional to S and it's proportional to I, and I take the product, and then I need some constant in there, some constant R that tells me to what extent it's proportional to the number of contacts between susceptible and infected individuals. And I call R the contact rate. So that's our first equation. Our second equation tells us how the number of infected individuals changes. And so there are two things to think about here. One is, from the first equation, if a susceptible individual becomes infected, then that will increase the number of infected individuals. So di by dt, the rate of change of the number of infected individuals, is going to be equal to R times S times I. But then there's another thing to consider, is that individuals may be cured or vaccinated or in some other way removed, and the number of individuals who are cured in this way should be proportional to the number of infected individuals. And so if we're removing infected individuals from the population, that should be a negative sign, and it's proportional to I. Constant proportionality is some constant A. And I call A the removal rate. So now we have two differential equations, and you can see that both of them depend on each other. I can't solve one of these two equations in isolation, because to solve the second one I need to know how S is changing, but to solve the first one I need to know how I is changing, because they appear on the right-hand sides. And finally, how does the number of removed individuals change? Well, that should be exactly the balance that we have when an individual is no longer infected but cured. They should just add the dr by dt, the rate of change in the number of removed individuals. So that is my system. But in fact, the third equation for the rate of change of R decouples. Once we've found I, then we can find R. So I'm not going to consider that third one anymore. What I'm interested in is these two coupled differential equations. So I have some questions for you. I claim that the number of susceptible individuals is always decreasing. So why is that? You can put your answers in the chat. Yeah, there's some good answers coming up. That's right. So mathematically, I would say R, S, and I are all positive, and the minus sign means that S, ds by dt, has to be negative. But you can think about the modelling, and yes, once you've gone from susceptible to infected, you can't come back in my model. And of course, maybe that's something we should change, but let's see what the consequences of this model are. And so every individual goes from S, possibly to I, and then possibly to R, but they can't go back. So S is always decreasing. Good? Under what conditions does the number of infected individuals grow? Another question for you. Or to put this another way, right, so if R is large, Yeah, so Sam has said we need RSI greater than AI. That's the important thing. That is, we're asking when is the rate of change of I positive, and that's if I times RS minus A positive. Well, I is necessarily positive, so this means that we need S greater than A over R. And so you see that there are two parameters, but the important thing is their ratio. The ratio of the removal rate to the contact rate. And that's key. That's the key idea from this model. And yet we've not solved anything to come to this conclusion. We've just looked at the equations. Third question. This is a hard question. Why does the number of susceptibles never reach zero? So I'm going to let you think about that. And I'll come back to it at the very end. I've told you I'm not going to solve these, but I am going to sketch what I think the solutions look like. And I'm going to use axes of number of infected individuals against number of susceptible individuals. And I make a few claims about how to do this. So for any initial condition, and my initial condition must start on this diagonal line at t equals 0, there is a unique line that tells me the evolution of I and S in time. And to do this properly, I'm not going to prove it to you now, I'm just going to tell you that lines can never cross if I and S are non-zero. So what do we know? Here we know that S, for my initial condition, S naught, I naught, S naught is less than A over R. That means that I is decreasing, and we also know that S is decreasing. So I can draw a line that does that in time. And eventually I end on the axis with S non-zero, but I does go to 0. This is good news, right? As time progresses, the number of infected individuals in this model will go to 0. And so I can choose a range of initial conditions on this diagonal line, and they'll all do something similar. Unless my initial condition has S naught greater than A over R. And then in this case, we know that to start with, the number of infected individuals must increase until we reach A over R, and then decrease. And so this is an epidemic, because the number of infected individuals is rapidly increasing. This is what we want to avoid. So this example was for large A over R. What about if I have a small value of A over R, this ratio of removal rate, contact rate? Well, again, if I start with S naught less than A over R, S decreases and I decreases. You can see that if I start with large S, much greater than A over R, I'm going to increase the number of infected individuals greatly before we get to so few susceptible individuals that the number of infected individuals starts to decrease. So if A over R is low, we have a large epidemic. That's the message. To avoid a large number of infections, we keep A over R as high as possible. What does that mean? And some of you have been trying to answer this in the chat. Either we keep A large, that's with good medical care. A good removal rate means that people are cured very quickly, or they're vaccinated. Or we can have large A over R by having R small. And that means reducing contact between individuals. So, my conclusion, we've not had to solve any equations to reach these conclusions. Just been analysis of the equations we've written down. And for me, the graph really helps me to figure out what the system is predicting. But of course, there are further effects that one might add, and in fact, people are adding them and taking them into account. Okay, let me look briefly at the chat to see if anybody has any good ideas about why the number of susceptibles never gets to 0. Yes, I find it hard to rationalize this in words. Let me show you an equation, and apologies, this really does require some calculus. I divide ds by dt by dr by dt, and that gives me some equation for ds by dr, the rate of change of susceptibles with the number of removed individuals, and that's an ordinary differential equation that I can solve, and it's an exponential, so s decreases exponentially, and if you've met the exponential function, you know that the exponential never goes to 0, as in this case the number of removed individuals tends to infinity. So another conclusion, but that did require some more advanced calculus. A disease is eradicated through a lack of infected individuals, not susceptible individuals. So it's a simplified model, but there you go. There's another interesting conclusion of one piece of mathematics. Now, of course, you're going to have related this to the situation that you find yourself in. And so maybe we've got time for a few minutes of discussion on how you might apply this sort of model. So I'll stop there, Andy.
Thanks, Simon. Questions. Thanks, Simon. Any comments or questions at this point, folks? If not, we'll move on. Shall we? There'll be another chance. Oh, hold on. We've got a question here. Could R also include deaths?
Indeed, it could. I've tried to avoid that. It's not a jolly subject to talk about, but removed, yes, it could include deaths.
And Cassie's asking, in order to study this, would you need any knowledge of biology, or is it purely mathematical?
You do need knowledge of biology, and I haven't tried to estimate R or A, and I don't think I should. I think that requires biological input, or in this case medical input. Try and estimate the contact rate, try and estimate the removal rate. And that's true more widely of this module on mathematical models of biological systems. It's aimed at mathematicians. It's about dealing with equations, but all of the constants and things that we put in all have to be estimated by biologists in the wild. So that's very important. And so there's a lot of work in the UK mathematical biology community where the idea is to bring mathematicians and biologists together, which is difficult because you have to find a shared language where you understand each other, but is vitally important to make these models applicable and useful. Good question.
Simon, should we move on to Kim's presentation and then
okay.
Look at the questions all together at the end, just to make sure we're good for time? Is that a good point to bring you in, Kim?
Yes, certainly. That sounds good. Right. That worked okay?
Great for me. Yep, we're good.
Good. Right, so I'm Kim Kenobi, and I'm a statistician. So Simon has given a mathematical perspective on this, and I'm going to talk about things from a statistical point of view. And I'm going to think about testing for diseases. Again, it could be general, but I'm going to apply it directly to the coronavirus testing. So the scenario I want you to consider is that you've gone for a coronavirus test. For whatever reason, you decided you needed a test. And as this table shows, there are 4 possible outcomes. So either you have the disease or you don't have the disease, which are my 2 columns there. And then either the test returns a positive result or it returns a negative result. So if we look first at the top left-hand corner, you've got a positive result and you do have the disease, so that's a true positive. And then in the bottom right-hand corner, you don't have the disease and you get a negative result, so that's a true negative. And if the world were perfect, or if these tests were perfect, that would be all that you would have. You'd have zeros in the other places. But they're not perfect, so sometimes you might have the coronavirus and get a negative result, which is a false negative. And sometimes you might not have coronavirus and it returns a positive result, which is a false positive in that case. What we're going to think about is this question. You've gone to have your test, and then maybe half an hour later you get a text and it says you've got a positive test result. So should you be concerned? So what we're thinking about is, if I've got a positive test, have I got the disease? That's what we're interested in. Right, I'm going to introduce here the idea of conditional probabilities. And we'll see this in a sort of picture on the next slide. But for the time being, we're going to introduce this language of the probability of A given B. So A and B can be anything. Those are just any events we might be considering. And I've got 4 probabilities here. So the probability of C given plus, C given minus, NC given plus, and NC given minus. And this is relating back to this C and the no, so C and NC having the disease and not having the disease, and plus and minus being the test results. So could you put into words what each of these represents? So just have a little bit of a think about that, and maybe choose one of them, and if you put in the chat how you would put into words what that means. Let's say P C given plus. What does that mean in words? Could somebody put that in the chat?
Done silence. Oh, hold on.
Well, that's okay.
Hold on. P C given plus means probability you have actually have COVID given you have a positive test result.
Perfect. That's exactly right. We'll stop there because that's the main one I want to focus on. So that's right. So what's the probability you have the disease given that you've obtained a positive test result? And you could translate the other ones similarly. But we're going to focus on that first one, the probability of the disease given a positive result. Now, I imagine most of you have seen a Venn diagram at some point. So we have circles A and B representing 2 events, A and B. And then we might look at the overlap of those events. So A and B both taking place. You may wonder why I'm doing this both ways, but you'll see in a minute. So if we think about the probability of A given B, it means that we're assuming that B has taken place. So we want to have the probability of B on the denominator, on the bottom line of our fraction. And what you might talk about is restricting your universe to B having taken place. And we can also do it the other way around. The probability of B given A is the probability of both of them divided by the probability of A. So we're restricting our universe to A in that case. Now, the only reason I've put both of these in here is because you can see that the probability of A and B occurs in both of those expressions. And that's important for something called Bayes' theorem. So there was a statistician called Bayes, and his result allows us to relate the probability of B given A to the other way around, to the probability of A given B. And that particular relationship ends up being fairly straightforward. The probability of B given A is the probability of A given B times the probability of B divided by the probability of A. Okay, so we've got a way of relating these two conditional probabilities one to the other. Okay, well, we've got a bit of probability theory going on there. How does this help us with the coronavirus test question? And that's a rhetorical question. I'm not expecting an answer to that one. Let's have a look and see how it helps. Let's return to our table again. So we've got this 2x2 table of all the 4 possibilities when you have a coronavirus test. And I'm going to assume we've got a population of size 100,000 people. I apologise for the dog in the background. So suppose that in our population, 1% of the people have the disease. This is called the prevalence of the disease. So we've got a prevalence of 1% in this case. Now, I'm going to introduce 2 terms here, which if you do any research at all on biological tests, you'll encounter these terms. So the first is the sensitivity of a test. Now this means if you have the disease, what's the probability that you get a positive result? And in this case, I'm going to assume 94%. So if we take the true positives and divide by true positives plus false negatives, we get 0.94. The other number is the specificity of the test, which means if you don't have the disease, what proportion of people return a negative result in that case? So if we take true negatives divided by true negatives plus false positives, I'm going to assume that's 0.95 in this case. So let's see if you can understand what I've said to you here. So given this information, what are the following probabilities? Firstly, what's the probability of no coronavirus? So if you randomly choose a person, what's the probability that they do not have coronavirus? Can somebody pop that in the chat?
We've got Sam saying 0.99.
Yeah, that's right. That's exactly right. Yeah. So 0.99, it's 1 minus the prevalence in that case. You either have the disease or you don't. 1% of people have the disease, so therefore 99% of people do not. And then this one, I've used a notation here where I've got a vertical line to mean given. So what's the probability of a positive test given that you have coronavirus? So the probability plus given C. How can we use those numbers? Or which of those numbers is that thing here?
We've got 94% or 0.94 is strong consensus there.
Yeah, the strong consensus. Good, exactly. So 94% is telling us that's the probability of a positive test given that you have the disease. That's great. Right, so we've got the probability of plus given C. So the probability of a positive test given that you have the disease. But we want it the other way round. We want to say, given that you've got a positive test, what's the probability you have the disease? So I'd like all of you to have a go at this question and throw a number in the chat. So considering the numbers given in the previous slide, what does your intuition say about what value this probability might be? So we want a number between 0 and 1, which is the probability you have the disease given a positive test. Don't think about it too much, but what probability do you reckon that might, what sort of area of probability might we be talking about? So are we getting a range of answers there, Andy?
We're not yet. No, very low. The first response, 18%. 0.1 says Libby.
Oh.
0.09 suggests
okay.
Phoebe.
Oh, we're getting some very small numbers. Okay.
Yeah.
That's interesting. That's interesting.
0.9. Yeah.
Okay, so I mean, we're saying that there's 94% sensitivity, 95% specificity, but you clearly think that there's not much of a chance that you've got the disease if you get a positive test. Okay, let's see how the numbers behave.
Lucy's come in with a 0.4.
A 0.4, okay. Okay, great. So we've got a range of values from quite low, 9%. Has anybody put anything in the 90s, Andy, or is it all quite low? Anything in the 90s?
No, and then there's one more than 0.9, 0.8.
More than 0.9. Okay, so we've got a whole range from less than 10% to right above 90%. So clearly, yeah, you're thinking widely about the possibilities there. Let's see what the numbers tell us. We've got a prevalence of 1%. As we've said, therefore, the probability that a randomly chosen person does not have coronavirus is 99%. The probability of a positive test given you have the disease is simply the sensitivity, so not 94%. And the probability that you have a positive test if you do not have the disease is 1 minus the specificity, so it's 5%. Right, so now we're going to use Bayes' theorem. The probability that you have the disease given a positive test is the probability of a positive test given coronavirus times probability of coronavirus divided by the probability of a positive test. And I'm not fully going to explain what happens on the bottom line here. It's something called the law of total probability, but basically the probability of a positive test can be divided up into two bits. The probability of a positive test given coronavirus times the probability of coronavirus plus the probability of a positive test given no coronavirus times the probability of no coronavirus. So when we put in the numbers, we end up with about 0.16. Well, this is kind of in the range that some of you went for in the end. I was hoping I might fool you and that you might all think that it was going to be above 90, but you sort of preempted me with your low responses there. So is this result surprising? What is it saying? Well, it's saying that if you have a positive test, the probability that you have coronavirus is only about 16%. So it's only about a 1 in 6 chance with the numbers that I've included here. So why is this going on? What's happening? Has anybody got any thoughts as to why this 16% is so much lower than the 94% or the 95%? Can anybody articulate why it's quite a low number in this case?
Nancy Abrams saying because so many more people without COVID, there's so many more people without COVID than with. So few people have the disease. Yeah.
That's exactly right. So we've got a lot of people who do not have coronavirus, and the false positives is what's kind of skewing the result in this case. So let's just have a look at that table again we had at the beginning. We've got our 100,000 people, and we're saying 1% of those, so 1,000 people, have coronavirus. Therefore, 99,000 people do not have coronavirus. So using the sensitivity and specificity of the test that I'm considering, how many people would we expect in each category in our table? So here are the numbers. 1,000 people have coronavirus. 99,000 people do not have coronavirus. So out of the 1,000, 940 test positive. But out of the 99,000, 5% test positive. So we've got 4,950 positive tests, which are false positives. So the relevant calculation is 940 divided by 5,890, which is about 16%. Right, what's the take-home message from all of this? Well, clearly, a positive coronavirus test result doesn't necessarily mean you have coronavirus. Note, this is only true if the specificity is less than 100%, because it's only when the specificity is less than 100% that you get some false positives due to false positives. And using the numbers that I've given you there, there's only a 1 in 6 chance that you have coronavirus if you test positive. So in the words of the Hitchhiker's Guide to the Galaxy, my advice if you get a positive test is don't panic. Okay, thanks very much. I'm happy to take some questions. I'll stop sharing my screen so I can see what's going on in the chat.
Thanks, Kim. There's a question here from Cassia. Do you think this could be increased because you are not testing everyone?
Do I think
As
this
in-
could be... What could be an increase? Sorry,
We
Cassia.
need some clarification on that one, don't we, Cassia? If you could let us know. Let's take another question. Let's whiz back to some questions that came in during Simon's session, if that's all right.
Yeah.
And then we'll come back to that. There was a question here from Sam to Simon. Are there links with chemical reaction rate equations, like people infecting other people, which could be analogous to a chemical reaction, and removals analogous to formation of products, and populations are analogous to chemical concentrations?
Indeed, there are.
Question.
Yeah, it's a very good question. There are. And so chemical rate equations, a molecule of A and a molecule of B combine to make a molecule of C, occur at some rate, and you describe that using a differential equation. And so the mathematics underneath this is almost identical, and it's just the context that's different. The application I like is if you think of these as molecules with different colours, and so as they interact, react, combine, you get different colours. And there's a wonderful article on how the leopard gets its spots in Scientific American, which explains how exactly these sort of equations can explain pigment in animal coats and the patterns that result.
Okay, thanks, Simon. I'm just whizzing back to Cassie's note here. Could the 16%, this is back to Kim's point, could the 16% actually be higher because the tests aren't being given to everyone? So P bracket C could be higher in this context. Does that make sense?
Okay. Yeah, let me try and understand what's going on there. So could the prevalence, the probability that somebody has coronavirus, could that be higher? Could the 16% actually be higher because the tests aren't being given to everyone? Yeah. I mean, if the prevalence has been incorrectly estimated, that would certainly change the probability of coronavirus given a positive test. So that's a partial answer to what you're saying there, Cassia. Yeah, I mean, I'm sort of assuming that the prevalence has been estimated independently somehow, and that somehow we have this sense that only 1% of the people have it. I'm not quite sure if I've answered your question there. Thank you. Shall I have a look at Phoebe's question? Do you think there is a way to decrease the probability of a false positive? Would fewer people being tested help decrease false positives? Right, Phoebe, that's a great question. So the probability of a false positive is a feature of a particular test. So I've read that commercially available tests have specificities which range from even as low as 85% up to maybe 99.9 or even very close to 100. So commercially available tests have a whole range of false positive rates, but the false positive rate is kind of an inherent feature of the test. And fewer people being tested would just mean your proportion of false positives would remain the same even if fewer people were being tested. That's an answer for Phoebe there. I don't know if there are any more questions for Simon rather than me hogging all the time. No, I'm happy to carry on.
There was a question about integrals. I'm just trying to find it now. Integrals instead of... Could you use integrals instead of differentials, says Sam.
In this context, I don't see how to, but in general, yes, when you want to somehow integrate over the whole population rather than model what's happening to one particular subset of the population, that might be a good way. But integral equations are much harder to solve than differential equations.
Cool, thanks, Simon. Should we jump back to some? Simeon's got a comment about the reliability of the numbers that the government's using at the moment. If tests are only true positive in 1 of 6 positive tests, did I get that right? Are you on that one?
Yeah, I'm on that one. That's fine. Okay. So yeah, that's a great question. So yeah, you're right. If the specificity of whatever tests the government are basing their numbers are on was as low as 95%, then a lot of the test results that are returned are false positives. I don't know what the government are trying to do. I mean, they've got very good people on this. In Imperial, there's a good group who kind of do a lot of the modelling for the government, and presumably, I don't think people are using these test results in isolation to make comments about the prevalence of the disease in the community, for example. So I think those, yeah. I mean, I think that the government's aware there are lots of people asymptomatic, for one thing, so that makes it more difficult to kind of predict the numbers of positives. I think it's Lucy's comment, Lucy McGinn, is this related? If we see 20,000 positive results, then should we actually be reading that only 16% of those people are actually positive? Yeah, I mean, I think, to be fair to whoever's trying to report these numbers, the specificity of the tests, of some of the tests at least, is very, very close to 100%. So some of the tests have got a very high specificity, in which case the number of false positives is much lower. But I think that, from my point of view, one of the main conclusions is that probably a lot of people are having to self-isolate when they don't have the disease. Is probably one thing that's going on. And I don't know enough of the detail about exactly how the government is counting these cases to know how they're interpreting these results. I mean, they'll notice how many positive results they're getting, but I don't think they'll assume that correlates exactly with the prevalence necessarily. Yeah.
Cool, thanks, Kim. It's coming up to 3 o'clock, which is when we said we'd end this session, but we will run on for a few more minutes just to get some of your questions answered. If you do need to run, though, to another session, then please, I've sent a link in the chat to a feedback session, so it'd be great if you could give us your thoughts and feedback on today's session. Have a great afternoon if you do need to run off. And thanks, guys, Simon and Kim at Aberystwyth, for running today's session. We'll just go back and answer a few more questions, if that's okay. There was a question here about yeah, what good free resources are there on mathematically modelling infection testing and pandemic spread? Is there anything that you know of that's a good resource out there?
I really like this book.
Oh, hold on.
Of course, it's not free.
It's
but if you
J.D. Murray's. Oh, there we go. J.D. Murray's Mathematical Biology. There we go.
If you can get your school library to subscribe to the online copy of that, you need a bit of calculus. Once you've done calculus at school, at college, then it's really good read.
And thanks. If you do need to dash, then thanks for being with us and have a great afternoon. Kim, you were going to tell us about a resource?
Yeah, there's a very straight. Well, I think it's a fairly straightforward chapter of a book which is freely available on the internet. It's called A Light Introduction to Modelling Recurrent Epidemics, and I think it's really accessible. Very
fascinating stuff, chaps. Any final thoughts from you both about the use of maths and stats in the current pandemic situation we're in?
There was a question earlier on about what mistakes were made in modelling the coronavirus epidemic, which I think is very interesting. I don't know exactly which model Sage were using, but the model is what the model is. And I think where mistakes enter is in 2 ways, really. One is not understanding what assumptions were made when you interpret the results, and the other being thinking that the mathematical model tells politicians what to do. The science is not telling them what to do, it's telling them what's happening and they have to decide what to do. So I think that's really worth thinking about. You could make the mathematical models as complex as you like with 100 parameters, and they could model something really, really accurately. But would that have any value? Would anybody understand it? Would anybody understand how to apply it to a different situation? I'm not convinced they would.
I think something I would add to what Simon's saying there is that what I've noticed in the last year or so, since we've been kind of grappling collectively with all of this coronavirus stuff, is just how public maths and statistics have become. I think so things like data science, for example, although people were beginning already to understand the importance of data science, it's now kind of a real buzzword, data science, in terms of understanding algorithms and statistics. And I think that the news reporting about the modelling that's been going on has raised the level a little bit in terms of the public's awareness of maths and statistics. And I mean, from our point of view, it's great. It's kind of people are realising the importance and the universal applicability of what we can do with maths and statistics.
Thanks, Kim. What about the general study of your topics at university? Any thoughts on the ideal routes or particular angles that you take at Aberystwyth in your relative fields in stats and maths?
Will I go first, Kim?
Go for it. Yeah.
Muted, I think. So I think you'd find that most courses in mathematics would give you a broad introduction to statistics, pure mathematics, applied mathematics, and then what you should be looking for is the sort of the specialist subjects that come in later on in the degree scheme. For example, Kim teaches a module in topics in biological statistics. As you've seen, I do something in mathematical biology. We're introducing new modules in information theory. We teach something on data science. So it's only after you've got over the introductory material that you need to think about what is it that is special about this place.
I'm trying to think what I can say in addition to that. Yeah, I mean, I think one thing that's quite important to think about when you're applying for universities is what size of university do you want to be part of? And I think there are benefits and disadvantages in huge universities, and there are benefits and disadvantages in smaller universities as well. In a huge university, I think it's in some ways less likely, unless you're very lucky, to find well, I think you're a little bit more anonymous in a really big university. There's so much going on in a huge university that although you might have a wider range of modules available, I don't think it's quite such an intimate experience. For me, I've moved from Nottingham, which was a pretty big university, and Edinburgh, as I've been in as well, which is a big university. And there's something very special about the kind of the community sense of a smaller university like Aberystwyth. And I think one of the reasons that our students report so positively about their student experience is because you know your lecturers very well and you're really part of a community. So I think that's definitely a benefit of being in a slightly smaller place.
Thanks, chaps. Any final questions from our participants out there? If you've got a microphone and you're happy to use it, you can just jump on that and ask a question if you're keen. If not, great to have you all with us today, and have a great afternoon if you're leaving us. And thanks to our speakers, Kim and Simon at the University of Aberystwyth Maths Department. Any final thoughts from you chaps? I don't think we've got any questions coming in, so.
Good, it's a good session. Lots of good questions in the chat.